Hello everyone, welcome to Automotive World. I'm Martin Carl, I'm Automotive World's editor. Thanks for joining us today for this webinar, which is all about co-simulation and how this can aid the development of applications such as hybrid electric powertrains. Specifically, we're going to hear today about FEV's co-simulation platform, xMOD. Hassen Hadj Amor and Morgan from Avicii of FEV will discuss how xMOD extends simulation to real-time applications with less effort. We'll also hear about how its high speed and memory combine to handle complex applications, including hybrid electric powertrains, and how this application fits the heterogeneous models for any simulation mode, allowing system and control engineers to start verification and validation phases early in the design cycle. We'll have a presentation of about half an hour, 40 minutes or so, followed by a Q&A. If you'd like to ask a question, please type your question into the Q&A box on your screen. We'll put as many relevant questions as possible to our panelists. We'll also make slides and a recording of the event available. We'll send you an email to let you know how and when you can access those once the event is finished. For now, I'm going to hand over to Hassen and Morgan for how co-simulation enables efficient automotive product development. Panelists, the floor is yours.
Thank you very much, Martin. So hello, everybody. So my name is Hassen Hadj Amor. I am a product manager for solution related to simulation and systems at FEV. And I will present this xMOD co-simulation platform, which enables efficient automotive product development. So I will be supported by my colleague, Morgan.
Hello, everyone. I'm Morgan. I will do a short demo of xMOD during this session, and I am mainly the product expert for xMOD. I am doing all the outline for the product.
Thank you, Morgan. So I would like to start this webinar with a video. It's a video better than 1,000 words.
Today, Jim is sad. Jim is a bright engineer at FEV. He's in charge of building the new powertrain for new vehicles, meeting the new RDE legislation, and a multitude of new worldwide pollutant emission regulations. And nothing works. He has one team to define the ECU control laws, one for adapting the engine and its after-treatment system, one for the gearbox, and of course, all these need to work correctly with different types of vehicles. All the design teams come with their models made from different software tools and absolutely unable to communicate. Fortunately, at FEV, they have xMOD. xMOD is a co-simulation and virtual experimentation platform. Combine your models and create the complete powertrain system using native co-simulation features and standards such as functional mock-up interface. Thanks to the power of calculation of xMOD, there is almost no limit. Now the design teams are happy and Jim too. The models in the loop operation is done. He can go to the next software in the loop step by integrating the models in standalone and check if the design operation has been done well. In a minimum time, he will be able to assess incredible numbers of scenarios. Due to the xMOD exceptional speed up 10 to 40 times faster than others, and much faster than real time. Hey guys, it seems that there is a problem somewhere in our simulation. What to do? Let's go back to my models, the so-called MIL step, and just modify my models accordingly. Replace my engine model. Wait a minute or two. And now it works just like that. Now Jim is eager to check if his design proposition will work in the real world. First step, test the ECU in the FEV HIL testbed in real time. And then check at the powertrain test bed. Imagine the time that Jim has saved. Without xMOD and simulation, it would be very difficult now to develop new powertrains, including hybrid and electric ones. What makes xMOD different is its heterogeneity and its hard real-time capabilities. Thanks to that, the models keep a same level of accuracy along the process. Consider all the functionalities and tasks you can do with xMOD. Imagine the gain of time for everybody at each step, from the design office to the control team, and then to the testing and calibration department. You can stay in the same environment, same models, screens, procedures, test cycles. Now, Jim feels relaxed. His team is happy. His customer will be happy, and maybe will buy an xMOD for his own.
So, I wish that you like this video, which resumes a little bit the xMOD platform concepts. So now I will go through this presentation and I will show you more things. So the content of this presentation will be divided in three main parts. The first part, I will explain what is the models in the vehicle development process applied currently at most of the OEMs, and what we propose based on our toolchain at FEV to solve many problems that we noticed during our projects that we made for our customers. Second part, I will introduce the xMOD co-simulation and virtual experimentation platform. So I will focus on the model in the loop and software in the loop. So I will show how to import models inside xMOD. Morgan will make a demo of that, and we'll show you xMOD, and we'll show a nice demonstration at the end. I will also explain what is the role of xMOD for real applications and what is possible and what is not possible using xMOD for real time. I will finish by presenting some customer use cases that shows a panel of cases that can be applied using the xMOD software. So let's start with this first slide, explaining the current process. So I think that you all know how this process is organized, mainly in three big steps. So we start from requirements until producing the final product. So from the requirement, we start mainly by doing modeling and simulation. So we have different departments working on different parts of the vehicle, and each department is using the best in class of the softwares, best in the market, and they have many engineers with high skills using their best software. So they have different type of formats. And this is the first step, which is the virtual integration. So they will try to do some co-simulation, I would say, so some integration of the systems together to understand the system. As the systems are becoming more and more complex, especially the vehicle, especially with hybrid technology, with ADAS technology. So it is more and more important to study the system early, to do full integration early. So this is the first step. The second step is more related to the mixed integration between the virtual world and the real world. So here I am talking more about real application, in which we have models running in real time and connected to hardware systems to do some validation, for example, rapid prototyping or function testing, etc. So at this level also, there is many tools. So the models are here. They are coming from different, as I said, different modeling software. There is also different hardware used from the most of the famous hardware on the market from many companies. And there is also a lot of different process. And finally, the last step is the hard and soft integration. So we integrate everything, the software and hardware to have the final product. So this is the classical process that we all know. We call it sometimes the V cycle, sometimes it's a regular cycle, etc. So what happens if during this process, and you are at an advanced level of testing your component, and you notice that you have a problem at this level? So you are too advanced in the step in the process. You are too close from the final product, and here you discover, unfortunately, that you have a problem, let's say, in your control strategy to control your hybrid strategy. So you have to roll back all the process, you have to go to the first step, open your Simulink model, maybe because I said it's a control model, so maybe it could be Simulink or other C code, or I don't know. And you use this model, you define it again, you change it, and then you have to again unfold all the process from the beginning with all the risks. Yeah. So this is we noticed that in our project that we made internally, that there is a lot of risks, waste of time. This process is working, but it is not smooth. It's a discrete process due to the heterogeneity of the softwares and the hardware, etc. So what we propose at FEV is to have a common, unique platform for models execution from the beginning, very early, from the model in the loop, software in the loop, until hardware in the loop, until the test bench. So what we propose is that you start designing your models, let's say for the control using, for example, MATLAB Simulink, for your vehicle, let's say using AMESim software, for your engine using GT Power, etc., etc. And early, you can start using one platform at this time to integrate your models, to do tool coupling, full integration, software in the loop, validate early your models, and then with the capacity to execute the models in real time, hard real time, you can go through this process step by step. And if you discover at a moment that you have a problem, as we said, so when you roll back the process, when you open your control model and you change the strategy, then you can test it in the same platform immediately. And you will, before unfolding all the process, you can know early in the process, it's the first step, if the last change that you made is efficient or not. And this is a big gaining time. And this is proven and during the many projects that we have made. So this is the development process for vehicle development process, and this is our solution for a smooth process, smooth transition to work on this process to bring your models until the test bed if you want. So here there is a resume about this multi-model integration and virtual experimentation platform. So xMOD, as I said, is covering many steps, starting from the model in the loop until software in the loop and hardware in the loop. So the first big feature for xMOD is the possibility to make the models working together. So you can use the best in class of your software to model your parts of the vehicle. Built by different person, you can use different language, and all these models can be integrated in one platform with different technologies that I will explain in the coming slides. Also, xMOD is a virtual experimentation laboratory. It means that once you add or you import your first model, you can immediately play it, plot it, add some instruments, and check it. The third advantage of xMOD, it's a feature which is very important. It's the core technology of xMOD is its extreme performance. Because in xMOD, we have highly optimized algorithms for advanced synchronization using multi-threading, multi-core, multi-solvers, etc. Also, there is a slide to explain this, and my colleague Morgan also will talk a little bit about that. So finally, xMOD ensures the continuity from model in the loop until hardware in the loop. You are using the same software, same platform, same technology, same license, and you can go from your models coming from the modeling guys, the simulation guys, until the test operators guys and the test bench. So you can use it during all the process. So this is an overview with some pictures that can resume on what I said quickly. So we have two, let's say, words. The first word is what is the virtual world, model in the loop, software in the loop. So we start embedding or integrating, importing physical and control models and trying to combine everything together. And here xMOD is defined as a standalone and tool coupling co-simulation platform. So by standalone, I mean something. By tool coupling also I mean something, and I will explain that. And xMOD can do both in the same time. And the second part or the second word is the real time. And here, when I am talking about real time, is hard real time, deterministic real time based on a real time operating system. And xMOD can be used as a real time simulation platform. And maybe you can see in this slide that we are using a laptop on the left, and on the right we are using a PC. It's a desktop PC equipped with a real time operating system. But the same application and the same models are used from the beginning until the end. So now I will explain how we import the models inside xMOD. So to get some models running in xMOD, we have there's three possibilities, three ways to do it. The first one, which is the basic one, that we selected since the beginning of xMOD 10 years ago, is to use what we call the MathWorks standard. So it means that our target that we provide to generate models for xMOD is based on the Simulink coder toolbox, formerly known as Real-Time Workshop. So if you have your model, let's say, this time I will talk about Daimola from Dassault Systems, so that you can export use model from Daimola as an S function to MATLAB Simulink. Once you have your S function running in MATLAB Simulink, then you can use the xMOD target. You can select the xMOD target, and you can generate by a compilation process a model for xMOD. So this model will contain two files, one XML file with the extension .xmodel and one DLL file. So the XML file is describing the inputs, the outputs, the parameters, signals, and many other features related to the model. And the DLL, it's a binary file representing the behavior of the model. So this model, once compiled and generated by a simple drag and drop, it can be used immediately inside xMOD, and you can play it. Of course, I've given this example of Daimola, but you can use also the same process with other software. So the second method for that is using the FMI standard. So in 2010, xMOD was from the first tools adapting the standard and participating to applying prototypes for the FMI, and still continuing to do that. So xMOD is supporting FMI for model integration, so FMI 1.0 and FMI 2.0, and also xMOD is supporting both types of the FMI for model exchange and the FMI for co-simulation. So the concept for the final users of the FMI is very simple. So you can export an FMU, which can have one of these specifications type or both together. So what is FMI for model exchange? It means that the model that you will generate from a modeling software will be called FMU, Functional Mockup Unit. This model will not contain a solver to solve the equations inside the model. So in that case, when you drag and drop such model, xMOD can detect it and will propose some solvers to be used inside xMOD to execute this FMU. So we propose some fixed step solvers and also some variable step solvers. For the FMI for co-simulation, we also in xMOD, when you generate an FMU from another tool with this type of specification, it means the solver will be embedded already inside the FMU. And when you drag and drop this FMU inside xMOD, xMOD can detect it and will execute this model without the need to use an internal solver inside xMOD. So this is also, this FMI integration comes to complete the first method, which is based on what we call the MathWorks standard. And the two methods can be used at the same time. It means I can embed a model generated with our xMOD target based on this MathWorks standard. And you can combine it with another FMU model generated from any software, and you can connect both models inside xMOD. And the integration is very smooth, and the models will look the same inside the xMOD platform. There is also a third possibility to get some models running inside xMOD. So the third possibility is based on what we call tool coupling co-simulation, because co-simulation can be divided in two types of simulation. The first one is what we call standalone co-simulation. It means the models are generated as files and are executed inside the integration platform. And sometimes to execute this type of models, you don't require to have the original tool installed in the same computer. We call this standalone co-simulation. So it is the first method of integration of xMOD, and some type of FMUs generated also can be executed without requiring the original tool. So another co-simulation method is called a tool coupling co-simulation method. And for tool coupling, it means the model that you will use will be executed in the original software. If we take, for example, a Simulink model, this Simulink model will be executed inside Simulink, and the other models will be executed inside xMOD. And xMOD and Simulink will communicate together and will advance their time during the simulation together and will synchronize themselves. And here I am giving some examples in which xMOD can be connected with other software like FlowMaster, Simulink, AMESim, or GT. This is here, xMOD is defined as a co-simulation bus. And what is great is that you can mix both. It means you can use a model that you compiled with your xMOD target. You can use an FMU model, and you can connect to another model that is running in another software. And xMOD can handle these three types of communications, execution of models in the same time. And I will give the hand to my colleague, Morgan. He will show you a few examples on how to compile a model to xMOD, how to use an FMU, and how also to use this type of tool coupling co-simulation. So Morgan, I will give you the possibility to do it.
Okay, thank you, Hassen. Okay, from my side, first I will present you the first way that Hassen presents you. It is to compile a model from the Simulink coder of MathWorks. Application. Okay. So first to all, I have a Simulink model, and inside this example, what I will do, I will compare a Simulink model that embedded the GT Power real-time S function. You can see it here. Before to try to compile the model, I need to configure a compiler. So there is some MATLAB command to do it. I just have the compiler already set, and after that I can compile the model. And there is some rules that you need to respect. It is some Simulink coder rules. So I need to check that my model have a fixed step solver. Okay. This is the only rule that I need to check before to compile. Here I will execute the model to check if it is running correctly. You can see that yes, it is running. I can check my result first. So maybe we will check the air mass flow rate. It seems good. So okay, now I can prepare the model to be able to compile. As there is a GT Power real-time S function, I need to configure some things, but it is very easy. I will go inside my Simulink browser. We have a block named Models Configurator. I will drag and drop it inside my Simulink model. Double click. It opens a GUI that I can configure, and I can see that I have a special option to integrate GT Power. I just check the option, and I can see detect the file used to be able to execute the GT Power model, and it detects also all the files that is requested to be able to compile the model. I close it, and I will just run the compilation process. I have the button here, I just click, and it starts the process. To follow what happens, I have diagnostics made by MathWorks. If I click, I can see all the lines that are written during the process. Okay? Oh, I think I have a problem. I will configure it correctly. What's happened? Sorry for this problem. I will check. Here I have this value, and I build. Okay. If the process is completely finished, I can see the 5 last lines that, okay, we success to complete all the procedure to build the model. If I check inside the MathWorks folder, I can see that there is some file generated by the model, by the compilation. I have the xModel that Hassen already described. It is all the signals and parameters and input-output of the models. And I have also the DLL generated. Okay. Now what I will show you, I will integrate this model inside xMOD. So I will start xMOD and share it. Okay. So I need to create a simulation. So I will go inside the simulation tab and I will create a new test simulation. It opens a complete simulation, but for the moment it is completely empty. I have what edition area where I can add some models. To add some model, it is very simple. I just need to go inside my libraries. It is the folder where I compile the Simulink models. You have the same name as the Simulink model. Just take this one and drag and drop inside the MIPS. It opens a block. Inside this block, I can see I have only one output. If I come back inside the Simulink model, I can see that I have only one output. So it is exactly the same that inside Simulink. If I want to have more details about this model, I can just double click. It will display a tree. I can see all the outputs, all the parameters available inside the model. It is all the gain, for example, here. And I have access to some signals also. Okay? If I want to be able to see the value, to control the value, etc., I just need to check a checkbox to create a quantity. It will give an access to the memory of the model. I can name how I want the quantity. Okay, so it is how to add what we call a native X model from xMOD, coming from the Simulink encoder and the xMOD target. Now, inside this simulation, if I want, I can add also a FMU. I go back inside my library of models. I see some FMU. I just take the FMU and I drag and drop inside the MIPS. I can see that this FMU, there is two possibilities, FMU for model exchange or FMU for cross-simulation. I can select model exchange. It will ask me for a solver. I can select the communication step, and if I want to activate some login. I have the FMU extract. I can see all the output, input. You have the model tree also to see parameters and signals. And if I want to connect to another model, I just drag and drop inputs to outputs and it will create the link between the model. So now the Simulink model compiled will exchange with the FMU. If I want to do the last way to integrate some model by doing tool coupling, I can directly drag and drop a AMESim model, for example. Okay, I have a special GUI to define all the options inside the AMESim models. I can select if I want to use the variable step solver or fixed step solver, and I will use the unfold option to see all the input-output as scalar. It detects all the names inside the AMESim models. I can change it if I want. And at the end, I have a block exactly like the other, and I can connect if I want by exactly doing the same workflow. So here you have an example where we mix the three cases: Simulink model compiled, FMU, and tool coupling co-simulation. Now, what I want to show you it is how to import a simulation inside xMOD. So Hassen already prepared a simulation and he sent to me. I will just import a simulation. I click on the button to import. I select like a zip that we prepare from his one version of xMOD, and okay, I import it. It finished to import, and now I have the simulation already prepared. If I open, I can see it is a complete simulation with a lot of different models, mixing GT power compiled model like I have done previously, Simulink model for control or for drivers, and a vehicle model coming from AMESim models. And I can directly, if I want, execute it. Will not save the previous one. Okay. Oh. I don't know why I'm not able to play. Strange. I have a problem on my PC. Maybe Hassen will play the demo on this PC. I don't know why, but I'm not able to.
No problem. Give me your hand.
Yeah, I will give you the hand back, Hassen.
Okay. Thank you, Morgan. Okay, so this is my screen, and now I am sharing the editor, the same application that Morgan was showing. So here there is some models combined together, vehicle model from AMESim, GT power model from GT, it's an engine model, mean value engine model, and some control and environmental model and driver model from Simulink. So let's run the simulation, and I have to share this. Okay, share, how to share. Okay. So Morgan, can you confirm that you can see the simulation running?
Yes.
Yes, okay. So here you can see this application that I designed for this webinar. So you can, as Morgan explained, you can use your instruments. You can use drag and drop your parameters, signals, inputs, outputs to animate and to interact with the models. You can have different views. For example, here on the on the vehicle, you can have a view on the driver or on the engine itself. So what we can see here, we have a speed set point coming from the control model, and we have here the vehicle speed that we measure, and you can see that the control is what we measure in the vehicle speed is following exactly the control. It means that our control strategy is running fine. So here you can see in the bottom, for example, we have many cycles. These cycles are, for the moment, implemented inside the models. So you can switch from one cycle to another one. You can interact with the buttons. So these buttons are developed by the xMOD engineer who who has done this application, who are integrated the models, etc. So it can be scalable, different from one application to another. It is not fixed. It is not developed by a software engineer. It's developed by simulation engineer. So I can stop, and I can here, for example, select FTP and start. So it will run another cycle based on FTP. You can see also some values, and you can interact completely with some parameters of the simulation to change them, for example. So that's all for the demo, and I propose to go back to the presentation. Okay, so the next slide is about the compatibility table. So this is a non-exhaustive list, of course, of some modeling and simulation software available on the market. So I have to remind that xMOD have a neutral position since the beginning, since 10 years ago. And here we are showing the compatibility with these tools based on 3 axes of comparison. So the first one is standalone co-simulation. It means using the xMOD target, using the MathWorks standard, and compiling the model, getting the DLL and the XML file, etc. So for that, you can see we are mainly compatible with many tools. The second axis of integration, it's the FMI integration. So here we are showing only part of these tools, but if you go to the website of the FMI standards, you'll see that there is a lot of softwares coming each year and supporting the FMI. So we cannot list all of them. The third axis is about this tool coupling co-simulation, which is a nice feature, but we are only doing this for Simulink, AMESim GT Power. So this feature sometimes can be requested by some of our customers, especially for control departments when they are designing the control model. So the engineer would like to keep working on his environment. Main of the time it's Simulink, and when he click on play on Simulink, it will run xMOD immediately. So the rest of the vehicle connected to the control inside Simulink, and he can debug inside Simulink. He can change a lot of things, and once the model is fixed and is giving good results, he can compile the model one time to get a standalone version. So it is also another possibility, and as I said, it is possible to mix the 3 type of models inside xMOD. So for the edition part, I think Morgan showed you also some features. So it is like in Simulink, you can drag and drop your models, you can connect them automatically, or you can connect them manually. So to connect them automatically means that there is some rules that you have to follow during the generation of the models. You can design your simulation, you can export your simulation to another engineer, you can import it, and all this, it is based only on one click. For the execution part, as I said at the beginning, this is the main core technology of xMOD. It's all in one tool to develop the application. So in xMOD, for each model is represented by a thread, okay? And each model also is represented by a solver. This solver could be a fixed step solver, a variable step solver. So it doesn't care for xMOD. So it's multi-solvers, and if the models are using different step times, different solvers, different threads, so they are fully also multi-core. So when we said xMOD is multi-core inside the model. So each model can be executed in one core on your computer. So if you have 6 cores computer, you have 6 models, so you can balance each model in one core. This is possible, and for that I am here writing load balancing. So it is also possible to give the possibility to xMOD to handle the execution of your models, so he can balance one model from one core to another one to speed up the execution. So when xMOD detects that the CPU time is not enough for your model, so he can balance it to another core. So this is really unique, and it's really performant inside xMOD. Also, you can save online your calibration for use. It means that you are working on your simulation, you are changing the parameters, etc., and you can save this calibration. You can export it, you can load it again if you run your simulation one time again. Of course, in xMOD you can develop your methods, and you can develop many scripts, and everything is drag and drop. You don't have to code anything manually. So this is an example about an engine model developed inside the AMESim software, and this model was not able to be executed in real time at our customer. So what we proposed is to split this model in 5 subsystems. So each cylinder was represented by a model, a submodel, and the air path also was split it in one model. So this complex model at the beginning required one fixed step solver at 25 microseconds to give accurate results. So using this possibility to split the models, so we helped our customer to split the model, to make it running inside AMESim first, to export everything to Simulink, to make the 5 sub-models inside Simulink running with the fixed step solver. So for the air path, we didn't use 25 microseconds. It has no sense. We used 150 milliseconds. So we relaxed the execution of the air path, and this is the benefit of using different solvers, different step times. And xMOD can handle that. And once you can see here in the middle the MIPS inside xMOD, which is, it means the big model inside xMOD, and you can see that you have the 4 cylinders and the air path connected all together automatically. And during the execution, it is multi-code, multi-threaded, and it was 25 times faster to gain real time. And it was able to use this model inside xMOD in hard real time without reducing the model, without using maps, for example. And you can check in Google to find a video to see it in YouTube, for example. And you have a live demo about connected this model to a microtobox. So now I will move to the final part, which is the xMOD hardware in the loop. So for each issue development stage, xMOD can be used. So we move now from the co-simulation on laptop and the Windows to co-simulation in real time. Hard real time. We have a real-time operating system controlling all the execution of everything inside xMOD. The models, the method around the methods, the instruments, etc. And you can do for that some rapid prototyping, functional testing, issue validation, etc. So the first use case coming from one of our customers is to validate this microtobox. A microtobox is an OpenECU. Maybe some of you don't know that. It's an OpenECU that can be used at the test bench, on the car, or in the office. Inside it, there is a control of the engine model, and our customer was using this at the test bed to validate the strategy for the control of the engine. So we helped him to develop a full powertrain model plus energy management. The models were very complex. You can see here all the MIPS, the big model inside, and we embedded everything in a standard PC. We equipped this standard PC with a real-time operating system, RTX. So RTX, it's just a level on the top of Windows. So Windows will run in one core and will take the control of Windows. So Windows cannot crash your computer or cannot interrupt the execution of the real-time operating system. And the real-time operating system will take the rest of the cores to execute the models, then to execute other operations. And using the CAN network, it was able to connect simply this microtobox to the xMOD standard PC, and it was able to establish a CAN communication to validate this control engine using a virtual simulation. So it was made on the office. So for our customer, before going to the test bed, it was an early validation made on the office using a microtobox with a desktop PC. It is not at all an industrial PC or hardware specific. It's just a standard PC. Of course, you can do, for example, some calibration. You can connect external tools like Inca to interact with the simulation of xMOD. If you don't like, for example, to use the dashboard inside xMOD, so you can use some softwares, for external softwares. A second application is for function testing. And this is one of the main applications used by xMOD. So some of the heat platforms available on the market are not able to maybe execute some type of models in real time. So xMOD is here seen as a compute unit that can execute the models in real time without reducing them, and we propose to connect this xMOD platform to these hill platforms using, for example, Ethernet here, or using EtherCAT, or using shared memory, fiber optics, etc. So there is a list of panels of protocols that can be used with xMOD. Another case is what we call engine in the loop. This is also a big success for xMOD. So what you can see here is a complete test bed. Here the automation system is the Morphy automation system coming from FEV, but it can be any automation system. It can be from other automation system, as I said, can be in-house automation system or from other in the market. So the automation system here, Morphy, is controlling all the engine, the ECU, the dyno, the battery, etc. And in xMOD, all the rest of the vehicle was designed. So a battery model, hybrid ECU controller, a vehicle model, the roads, etc. And everything is executed under real-time constraints. And xMOD can be just connected to this automation system, to the testbed, to make the engine behaving as it is in the vehicle. So the same application is now transformed in the next slide, in which we will replace this real engine inside the automation system by a modeled engine. So here you can see that for this case, the Morphy automation system is also able to run complex models in real time. And here we are transforming completely the real engine to a virtual engine, not only by using physical models, so in this case we used MATLAB and AMESim, but also to using some DOE models and statistical models to have better accuracy close to the real engine. So I will finish with the last slide before answering some questions. So here I am giving a future projection on the xMOD. So the target for xMOD is to be an open platform through standards, so we are working only on standards. xMOD can be used as a runtime simulator for software in the loop and hardware in the loop. So software in the loop, you can see here the laptop. It means the execution is as fast as possible, is under Windows, it's for simulation engineers, it's very simple. Hill runtime, it means that the models, it's a co-simulation, but the models are running on a desktop PC with a real-time operating system, and there is some boards to establish some hardware communication, etc. So you can see on the top, you have standards. So we are working on ASAM standards like XIL API, and we are working also on standards like FMI. So the goal is to give the possibility to third tools, party tools, to access completely to the simulation inside xMOD, to start a simulation, pause a simulation, play it, record it, and restart it, etc. So xMOD will be fully controllable and is already fully controllable from outside, from any external application. The only rule is that external application should follow these standards. So to finish, the final goal is to, in 2020, to have xMOD as a plugin software within a toolchain supporting all the standards. So thank you all for all your interest in this presentation. And now I think that, Martin, we can move to the question part.
Thank you, Hassen. Thank you, Morgan, for your time today. Thanks for sharing your insight. We do have about 9 or so minutes for questions. So if anybody would like to ask a question, please do type it into the Q&A box. We've already had some that have come in, so I'll begin with putting those to you. An interesting question from somebody who wants to know, is the co-simulation approach physics-based or data-driven?
Physics-based or, sorry, the second?
Driven by data.
Driven by data. It's a mix, I would say. It's a mix because Driven by data, yes, because we are exchanging the data between and signals between the models and doing some synchronization. But also, there is some part of physics because we have different solvers, and the solvers are handling state variables and handling events, and the solvers also. So this is physics-based. So it's both. It's a mix inside xMOD.
Okay, and a follow-on question from that: how is multiphysics and multiscale modeling at macro, micro, and quantum level related to co-simulation for automotive product development?
So the question is not very clear to me, to be honest, and maybe if it will be written, maybe we can answer later, but it is not clear.
Okay, sure.
Sorry.
All right. Is co-simulation compliant with Industry 4.0 and manufacturing companies?
I would say yes, it is compliant with Industry 4.0. And we can discuss more of this topic. It cannot be just answered like that.
All right, thank you. You mentioned 3 different methods during a presentation. Is it possible to combine them in one co-simulation?
Yes, of course. It is possible to combine the 3 methods. It means the compilation using the MathWorks standard, the FMI, and the tool coupling.
All right, and what are the advantages and disadvantages of using tool coupling, as you referred to it there, in co-simulation?
Yeah, so using the tool coupling can be benefit because you will use the original solver of the model. So it means if your model is designed in another software, and when you run it, you will use exactly the same solver, and you will get the same accuracy. The cause is that the co-simulation will not be speed enough. There is some slowness. And on the other hand, if the model is fully integrated, the advantage is that the simulation speed up is very good, but the accuracy is not the same as in the original software, because when you go through the MATLAB Simulink and you compile, you are using a fixed step solver coming from Simulink, and you have to use a small step time to adjust and to have close results than the original software.
Okay, well, given that this is an area of industry that I have no previous experience in, I'm going to read this question to you, and I hope it makes sense to you. Different models in co-simulation run at different speeds. The question has given an example of control models that run faster than plant models, such as GT. To accommodate faster control models, GT model often has to run in lower fidelity. Can you comment on this? And if that's not the case, how does the simulation realize this?
Okay, so maybe I didn't exactly understand the question, but I have an idea about it. It's about multi-rate inside xMOD. So of course you can use different step times, so different communication steps, and xMOD will be the chief of our orchestra to organize that. It's an internal job of xMOD to synchronize between the execution of the 4 cylinders with the control with the air path model, which are not running at the same frequency. So of course there is some techniques that we use inside xMOD to, like extrapolation, for example, etc., etc.
All right, thank you.
So I can see also a question about, I would like to ask about the AMESim engine example, where the 5 components, different Simulink blocks in xMOD. So, of course, we start from one model in AMESim. We split this model in 5 components. Of course, there is some know-how. We know that, for example, the air path doesn't require 25 microseconds. It has no sense. So we split it. We export everything to Simulink. So you have 5 components in Simulink, 5 models in Simulink. You connect everything in Simulink. You run if you have, because you will use here a fixed step solver. This is the problem of, or the problem between brackets, which is the disadvantage of using full integration. Then if you have good results at this time, then you can compile your 5 models inside xMOD, and you will be sure to have the same result that you have in Simulink. So of course, there is related to this also, I can see about boundary conditions. Yes, it's AMESim job. You have to handle that inside AMESim. Once fix it, then so it depends how to split, where to split, etc.
Okay. And somebody else has asked whether it's possible to perform co-simulation with CFD 3D models. There is some request for that, so it depends case by case. For the moment, it is not available, but for some internal projects, we are doing this for some CFD 3D models. All right. What are the protocols supported for xMOD hardware-in-the-loop applications?
So for the protocols, we have a panel of protocols available. So mainly we are using EtherCAT. So xMOD is EtherCAT master and EtherCAT slave. And also we are using UDP for real time. We are using shaded memory and fiber optics. So this is for the most performance and efficient protocols, but also we are supporting basic protocols that you can find in the automotive industry like CAN, FlexRay, etc.
Okay, well, just to wrap up, this is a presentation not just about co-simulation, but about how co-simulation applies to improving the efficiency of automotive product development. Can you give us some insight into how this co-simulation can benefit the end customer? Where in the sort of the development process does this co-simulation sit? And whilst the customer would never know that co-simulation has been done, how does what this offers benefit the customer at the end when they're in their car?
We started talking about the co-simulation since many years ago. So there is all technologies, new technologies like coming with xMOD, etc. But the goal is the same for co-simulation. Is to the systems and the vehicle or the cars are becoming more and more complex. So we agree all on that. And to understand such systems, we cannot focus only using modeling software to focus on parts of the vehicle. We have to understand all the vehicle. So here we start talking about co-simulation. So you need co-simulation early, since the beginning, since the model is ready. You can take the model and test it inside co-simulation platform. But this is not enough. It's not enough because you have to give a life of these models. These models will replace some real parts because you will do some hill applications, and you can also do some engine in the loop application. You will test your engine or you test your chassis, and for that you need to make some parts of your models virtual. And then you need a real-time co-simulation platforms for that. So this is how co-simulation in general, it is not only related to xMOD product, but this is how co-simulation and the real-time co-simulation enables the efficient automotive product development.
Excellent. Well, I think that's a really nice note to end on. Thank you very much to you both once again for sharing your insight with us. Thank you to everybody who joined us and all of those people who sent in questions. I hope that we've covered as many as you'd like us to in the Q&A. We've run out of time, though. Just to let you know, we will be making slides available and also an audio recording of the webinar. Well, not just an audio, a video, so you'll be able to watch it online. We'll send you a link to let you know how and when both of those are available. Other than that, I'd like to wish you a pleasant day, and we'll see you at the next Automotive World webinar. Thanks very much, and goodbye.